What can unfold in just 1 second? You could blink your eyes or take a single step, and in that same sliver of time, your heart can beat once. A second feels like an insignificant, fleeting instant. Yet I want to propose that our universe's history contains a unique second that held more transformations and mysteries than the entire 13.8 billion years that came after. What if the whole of our reality, including the fundamental laws governing the very matter you're made of, was forged in that unimaginably brief window? This isn't about the second after the Big Bang, but the absolute first second of existence, which raises profound questions. How could the cosmos be simultaneously infinite and yet contained within a volume smaller than an atom? And why does physics, which describes our world with such precision, fail completely when we attempt to look back at that very beginning? Let's venture together toward this ultimate horizon of time. Let's try a brief thought experiment to put things in perspective. Imagine compressing the universe's entire 13.8 billion year history into a single calendar year, from January 1st to December 31st. On this cosmic calendar, our own Milky Way galaxy wouldn't even form until May. Our Sun and its family of planets, Earth included, would only make their appearance in early September, with the first tentative signs of life emerging on our world by the end of that month. Following this scale, dinosaurs would have dominated the planet during the final week of December, only to vanish around the 30th. The entirety of recorded human history, from our ancestors' first steps on the African savanna to this very conversation, would occupy just the last few minutes before the stroke of midnight on New Year's Eve. Your whole existence is merely the final chime of the clock at the end of this cosmic year. It's easy to assume the most significant developments happen late in the story, but that is a profound illusion created by our human viewpoint. The truly pivotal event, the one that set the stage for this entire cosmic year, from the laws of physics to the particles of matter, happened in an infinitesimally small fraction of a moment right after midnight on January 1st. We are referring to the very first second of the universe's life, an interval so packed with radical changes, phase transitions, and the birth of fundamental constants that the billions of years following it seem like a slow, almost lazy, and predictable period of cooling. This was an era when the cosmos was transforming more rapidly than the human mind can possibly conceive. For many, the phrase Big Bang conjures a familiar image from popular science: an infinitely small, dense point, a singularity, that violently explodes into a pre-existing void. This cosmic bomb then scatters energy and matter, which gradually coalesce into the stars and galaxies we see today. While this picture is intuitive and aligns with our everyday experience of explosions, it is also, unfortunately, entirely wrong, and shares almost nothing with the modern scientific understanding of the term. This is where the subject becomes truly fascinating. Modern cosmology almost never employs the term Big Bang to signify a precise event at time zero. If you examine serious scientific diagrams illustrating the universe's timeline from institutions like CERN or NASA, you will not find a point labeled Big Bang. The name itself was actually coined by the British astronomer Fred Hoyle, an advocate for the rival steady-state theory, who used it with a dismissive and sarcastic tone. Despite its origins, the name stuck, but its meaning has evolved. The Big Bang theory is not an explanation for how the universe was created. Rather, it is a detailed framework describing how the universe evolved from an early, intensely hot and dense state into its present form. Think of it as a theory explaining how an oak tree develops from an acorn. It meticulously details every stage of growth, but offers no information about where the acorn itself originated. In the same way, the theory describes the process of cosmic expansion and cooling, but not the initial moment of inception. The crucial concept to grasp is that this was not matter expanding into an already existing space, like in a conventional explosion. Instead, it was the very fabric of spacetime itself that was expanding.
To better visualize this process, let's use the analogy of an inflatable balloon. Imagine drawing several dots on its surface to represent galaxies, and then begin to inflate it. You would observe that every dot is moving away from every other dot. Furthermore, the greater the distance between any two dots, the faster they recede from one another. Yet, not a single one of these dots represents the center of the expansion. The true center is inside the balloon, in a third dimension that is inaccessible from its two-dimensional surface. In a similar way, our universe's expansion has no center within our three-dimensional space. There is no single point from which everything erupted. The cosmos expands everywhere simultaneously, with the space between galaxies stretching like a rubber sheet, carrying them along for the ride. This revolutionary discovery made by Edwin Hubble in the early 20th century became the foundation of all modern cosmology.
At this point, another challenging question often emerges. If a vast amount of data, such as studies of the cosmic microwave background, the faint thermal afterglow of the Big Bang that permeates the universe, suggests that the cosmos is spatially infinite, how could it have once been infinitesimally small? How is it possible to compress infinity down to the size of a pea, or even smaller? This seeming contradiction finds its resolution through the introduction of a critically important idea, the concept of the observable universe. The reality is that our universe has been around for a finite duration, approximately 13.8 billion years. Compounding this fact, the speed of light represents the ultimate velocity at which any information can propagate through our cosmos. This combination of factors means that from our vantage point on Earth, we are limited to observing only those cosmic regions whose light has had enough time to reach us. Anything situated beyond this invisible boundary is currently unknowable, as its light is still on its journey. This personal sphere of visibility, what we call the observable universe, currently has a radius of about 46.5 billion light-years. Remarkably, this vast sphere, which contains no fewer than 200 billion galaxies, each composed of hundreds of billions of stars, was compressed into an unimaginably tiny space within its first second of existence. We have no certain knowledge of what lies beyond this observable realm. However, the most straightforward and elegant hypothesis suggests that it is simply more of the same universe, with the same kinds of galaxies and stars, potentially extending into infinity. This presents a striking paradox. The cosmos might be infinite, yet the portion we consider home once occupied a volume smaller than an atomic nucleus. The universe is not expanding into some pre-existing void. It is simply that the fabric of space itself is expanding. This fact, however, gives rise to another profound and logical question. If all the matter and energy of hundreds of billions of galaxies were once confined to such a minuscule volume, the density must have been utterly staggering, surpassing that of an atomic nucleus by trillions of times. Why then did the entire universe not immediately collapse into a single gigantic black hole? After all, Einstein's general theory of relativity predicts precisely this outcome for matter at such extreme densities. The key to this puzzle lies in a fundamental property of the very early universe, its incredible uniformity. For a black hole to form, you don't just need immense density, you need a significant difference in density from one place to another, what physicists refer to as a density gradient. It requires an extreme concentration of mass or energy in one region, surrounded by an area of considerably lower density. This contrast is what generates the severe curvature of spacetime that leads to a point of no return. Consider the analogy of a dam. It successfully holds back water only because the water level is high on one side and low on the other. If the water were at the same high level everywhere, there would be no net force or pressure differential. In the nascent universe, the density was colossal, yet it was virtually identical at every point in space. Essentially, there was no lower density area for any given region to collapse into, as every location was equally extreme. This idea, known as the cosmological principle, asserts that on large scales, the universe is homogeneous and isotropic, meaning it is uniform and looks the same in all directions. And it is a foundational concept in modern cosmology. Although there were minuscule quantum fluctuations in this near-perfect smoothness, which acted as seeds for the eventual formation of galaxy clusters, the universe was, on the whole, too uniform to collapse. Consequently, we must abandon the popular but inaccurate image of an explosion happening in an empty space. Instead, we are presented with a far more complex and fascinating narrative, involving a sequence of states, or what physicists call phase transitions, that the universe experienced in its first second. This is akin to investigating an ancient event, where the fundamental laws of physics and elementary particles are the only clues, and the scene of the crime is time itself. Our inquiry starts where our conventional physics and our very grasp of reality break down, at what is known as the Planck Wall. It is there, within the initial moments inside a seething cauldron of energy we can never hope to replicate, that the deepest mysteries about the origin of space, time, and the laws governing our world are hidden. To begin this investigation, we have to start by acknowledging the limits of what we know. Every journey has a beginning, but our journey to the start of time itself confronts us with a profound paradox. We encounter an impassable barrier not at the end of our path, but at its very inception. This is not a wall of brick or stone that can be touched or seen. It is a barrier woven from the very limits of our scientific understanding, constructed from the fundamental equations that describe our universe. Physicists have named this barrier the Planck Wall. It represents the divide between the cosmos we can, to some extent, describe and attempt to understand, and the absolute, incomprehensible mystery that lies beyond it. It is not a physical obstruction in space, but rather a conceptual boundary in our comprehension. To understand what this limit is, where it originates, and why it holds such importance, we need to briefly review two of the greatest intellectual triumphs of the 20th century. These are two distinct theories, each of which describes its own realm of reality with a level of accuracy that is both astonishing and almost unnerving. The first is Albert Einstein's general theory of relativity, published in 1915. This is the theory of the large-scale universe, the macrocosm, governing gravity and the way mass and energy curve space and time. It dictates the graceful motion of planets around stars, the gravitational lensing of light from distant galaxies, the space-time ripples created by merging black holes, and the expansion of the universe itself. In Einstein's framework, reality is a smooth, continuous, and flexible geometric fabric, where events are predictable and deterministic. The second major theory is quantum mechanics, which was developed in the 1920s by an assembly of brilliant scientists like Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and Paul Dirac. This is the theory of the incredibly small, the microcosm, describing the world of subatomic particles such as electrons, quarks, and photons that constitute everything we see. In this realm, probability, randomness, and fundamental uncertainty are the ruling principles. Energy exists in discrete packets known as quanta, Particles can behave as both waves and particles, and they can even exist in multiple places at once until they are measured. It is a strange, non-intuitive world that defies common sense, yet it works with flawless precision and provides the foundation for all of modern chemistry, biology, electronics, and computing. Both general relativity and quantum mechanics stand as monumental achievements in science, each validated by a vast number of experiments and making predictions of astounding accuracy. General relativity, for instance, forecasted the reality of black holes and gravitational waves long before we could ever detect them, while quantum mechanics anticipated the discovery of antimatter. Yet these two pillars of our cosmic understanding are fundamentally at odds, which is arguably the greatest challenge in all of modern physics, as they appear to describe two utterly different realities in two incompatible languages, one of deterministic geometry and the other of probabilistic algebra. When we apply these theories within their separate domains, with one governing the scale of galaxies and the other the realm of atoms, they work flawlessly and never clash. The conflict arises when you must describe an object that is simultaneously incredibly massive and infinitesimally small. This is precisely the state our universe was in during its earliest moments, possessing the immense energy and density of a giant star's gravitational field, all while being compressed into a space trillions of times smaller than a proton. This is the unique environment where gravity's influence is so immense that it cannot be overlooked at the quantum scale, and where quantum phenomena are so potent they must inevitably distort the very fabric of spacetime. When we attempt to use both theories in this scenario, their mathematical foundations collapse, yielding nonsensical results like infinities for density, temperature, and spacetime curvature. In the world of physics, an infinity is not a solution but a warning siren, signaling that a theory has hit its limit and is incomplete. The concept of a singularity, often invoked to describe the universe's origin, isn't a physical entity, but a mathematical placeholder, an admission of our own ignorance on the theoretical map. This frontier of our knowledge is defined by a specific set of numerical values, named for the German physicist Max Planck, who inadvertently laid the groundwork for quantum theory in 1900 while tackling the problem of black-body radiation. He discovered that three fundamental constants of our universe could be interwoven: the speed of light, which links space and time, the gravitational constant, which dictates the force of gravity, and his own Planck constant, which sets the scale for all quantum effects. Together, these form the Planck units, which delineate the very boundary we cannot yet cross. Planck time is the first of these units, measured at 10 to the negative 43rd power seconds. This duration is so incomprehensibly brief that more such intervals would fit into a single second than the total number of seconds that have elapsed since the universe began. It is widely regarded as the smallest increment of time that holds any physical meaning, suggesting that to speak of anything shorter would be as nonsensical as attempting to move half of the smallest possible distance. Next is the Planck length, a distance of 10 to the negative 35th power meters, which is trillions upon trillions of times smaller than a proton. To give you a sense of scale, if you were to magnify an atom to the size of the entire observable universe, the Planck length would be roughly the height of an average tree. At this level, our conventional understanding of space as a smooth, continuous expanse almost certainly fails. It is highly plausible that spacetime's fabric is actually discrete, or as physicists term it, quantized. Much like a digital image on your screen that appears continuous from afar, but is composed of individual pixels up close. The Planck length could very well represent the size of a single fundamental pixel of our reality. Finally, we have the Planck temperature, an astounding 10 to the 32nd power Kelvin. This temperature is so extreme that the energy of any single particle would be equivalent to that of a microscopic black hole, causing spacetime itself to effectively boil. These conditions are so far beyond anything we can replicate that they exist only in the realm of theory, describing a state of matter and energy at the absolute dawn of time.
This leads us to the Planck epoch, the period from the theoretical moment of creation up to 10 to the negative 43rd power seconds. Throughout this era, the entirety of our observable cosmos was contained within the Planck length and seethed at the Planck temperature. It was a reality where quantum effects and gravity were equally powerful and fundamentally intertwined, transforming the elegant, smooth sheet of Einstein's spacetime into a chaotic, turbulent maelstrom that physicist John Wheeler famously termed quantum foam, where space, time, and causality were in constant flux. To accurately describe this primordial state, we require a completely new theory, capable of unifying general relativity and quantum mechanics into a single, cohesive framework. This pursuit for a so-called theory of everything, or quantum gravity, is the ultimate goal of modern theoretical physics. Several promising candidates exist, such as string theory and its successor M-theory, which posit that fundamental particles are vibrating strings in higher dimensions, and loop quantum gravity, which suggests space is woven from a network of discrete quantum loops, though none have been experimentally confirmed. Therefore, the Planck Wall should not be seen as the definitive beginning of the universe's story. Instead, you should think of it as the end of the chapter that we are currently able to read, written in the language of a physics we have yet to fully comprehend. This is the frontier, beyond which quantum gravity reigns, a domain where our conventional ideas about space, time, and causality, and even the very number of dimensions in reality, could prove to be entirely naive. Attempting to look past this barrier is like trying to decipher the opening sentence in the story of the cosmos. While we currently lack the proper language for it, we can lean on hypothetical theories to envision what transpired in that roiling haze during the first 10 to the minus 33rd power seconds of all existence. Picture an ocean caught in the most violent tempest you can possibly imagine, but then dismiss the thoughts of water and wind. In this primordial storm, the very substance of reality is the volatile element. Space and time cease to be the static, unchanging backdrop for events that we've understood them to be since Newton's era. Instead, they become the sole, dynamic protagonists, boiling, frothing, and contorting into inconceivable geometric forms as their structure shifts in constant, chaotic flux. This analogy serves as the best, though likely the most inadequate, approximation our minds can conjure for the Planck epoch. This was the universe's inaugural moment, spanning from a theoretical 0 to 10 to the minus 43rd power seconds. You are stepping into a reality where the laws of physics had not yet been conceived, and where the fundamental concepts of here versus there and before versus after were stripped of all conventional meaning. It is an exploration into the bedrock of being, to a time before reality had settled on its final form. To truly grasp just how alien and profoundly different this early cosmos was, it helps to review the principles that orchestrate our universe today. These are the four fundamental interactions, or forces. Gravity, the most feeble yet infinite in its reach, holds you to the Earth, keeps planets tethered to their stars, and binds galaxies into immense clusters. Electromagnetism is far more potent, governing light, electricity, and all the chemical bonds that constitute the world you see. The strong nuclear force, immensely powerful but confined to the atomic nucleus, glues quarks together into protons and neutrons. Lastly, the short-range weak nuclear force drives certain forms of radioactive decay, and is essential to processes within stellar cores.
In our modern universe, these four forces operate as completely separate entities, seemingly bearing no relation to one another. Their strengths differ by dozens of orders of magnitude, and they vary in their effective ranges, their carrier particles, and the types of matter they influence. Together, they construct the intricate yet apparently disconnected architecture of our reality. However, driven by an almost aesthetic certainty in nature's underlying simplicity and elegance, physicists have long theorized that this separation is just a mirage, an artifact of our cold, low-energy existence. Think of it like frozen water which can form intricate and asymmetrical snowflakes. Yet, in its fundamental liquid state, it remains simple and uniform. In the same vein, scientists propose that within the extreme temperatures and energies of the universe's earliest instance, these four forces shed their distinct identities, their differences dissolved, and they merged into a single, unified, and perfect superforce. This is the state that defined the cosmos during the Planck epoch. The Planck epoch was precisely the era when this absolute, flawless symmetry dominated the universe, and all four interactions were simply different expressions of one unified fundamental entity. Because we still lack a complete and experimentally confirmed theory of quantum gravity, any portrayal of this period remains in the realm of educated conjecture. These are not mere flights of fancy, but are instead rigorous mathematical hypotheses built upon the theories considered our most promising candidates for explaining such an extreme state of reality. Let's examine what the two primary contenders for the title of A Theory of Everything suggest about this era. The most renowned candidate is string theory, which is built on a concept that is as elegant as it is radical. It posits that the universe's elementary constituents are not the dimensionless points assumed by the standard model of particle physics. Instead, string theory proposes that everything is made of minuscule, one-dimensional, vibrating filaments of energy, known as strings. Much like the different vibrations of a violin string create distinct musical notes, the various vibrational patterns of these elementary strings manifest to us as different particles. One mode of vibration appears as an electron, another presents as a photon, and a third as a quark. In this framework, even the hypothetical graviton, the particle that transmits the force of gravity, emerges naturally as a specific vibration of a closed-loop string. One of the most startling and enigmatic consequences of string theory is that its mathematics holds together only if the universe possesses more dimensions than we are able to perceive. Although the exact number can differ between versions of the theory, it typically points to 10 or 11 dimensions in total, 9 or 10 of space and 1 of time. This immediately prompts the question of where these extra dimensions could be, and why you only experience 3 spatial dimensions, length, width, and height, plus the forward march of time. String theory provides a sophisticated explanation. The additional dimensions are compactified, curled up into incredibly small, intricate shapes called Calabi-Yau manifolds, which are completely invisible to us. Their size is on the scale of the Planck length, making them far too small to be detected by any experiment. To visualize this, consider a thin garden hose. From far away, it looks like a one-dimensional line, but for an ant walking on its surface, it clearly has a second, circular dimension. In a similar way, our universe might possess these extra, curled-up dimensions that escape our direct observation. Though during the Planck epoch, when the entire observable cosmos was itself just the size of the Planck length, it is possible that all 10 or 11 dimensions were on an equal footing. In the very beginning, there was no difference between the vast, familiar dimensions of our world and the tiny, curled-up ones proposed by theory. They were all equally significant and deeply interconnected. It's possible that the event you know as the Big Bang was actually the moment this multidimensional symmetry shattered for reasons that still elude us. As a result, 3 spatial dimensions began to inflate, unfolding into the universe you see, while the others remained forever confined to the microscopic realm. This represents one of the most profound and thrilling ideas in modern physics, that the dimensionality of our space is not a fixed constant, but rather the outcome of dynamic evolution, a sort of cosmic fluke. The second leading contender, loop quantum gravity, presents an entirely different yet equally revolutionary vision. In contrast to string theory, it doesn't necessitate extra dimensions, nor does it attempt to unite all forces into a single framework. Its more focused objective is to quantize gravity itself, thereby bridging the gap between Einstein's geometric description of spacetime and the principles of quantum mechanics. According to this theory, space is not the smooth, continuous expanse you might imagine, but is instead discrete, constructed from indivisible quantum units, or atoms of space.
These fundamental cells are linked together into an intricate and ever-changing web known as a spin network. The evolution of this network through time, with its constant reconfigurations, is what you perceive as the fabric of space-time. The size of these elemental units is on the scale of the Planck length, and the smallest possible area corresponds to the Planck area. In today's cold and stable universe, this network is highly structured, appearing on a grand scale as the smooth, nearly flat, three-dimensional space that general relativity describes so effectively. However, under the extreme conditions of the Planck epoch, this network would have been utterly chaotic and disordered, resembling a turbulent boiling liquid more than an orderly crystalline structure. The connections between the individual cells of space would have been in constant flux, perpetually breaking and reforming. Within this framework, a singularity is impossible, because space cannot be compressed into a point of zero volume. It is fundamentally composed of these finite, though unimaginably small, atoms of space. What you call the Big Bang might, in fact, have been a big bounce. It's conceivable that our expanding universe was preceded by a contracting one. This previous cosmos collapsed until it reached a maximum, yet finite, Planck density. At that point, powerful quantum gravitational effects would have triggered a rebound, forcing it to begin expanding once more. This theory introduces the fascinating possibility that our universe existed before this pivotal moment, and that its birth is merely a single chapter in an eternal cycle of cosmic contractions and expansions. Regardless of which of these theories, or perhaps a third yet undiscovered one, ultimately proves correct, the majority of physicists concur that during the Planck epoch, spacetime was fundamentally unstable. It seethed and fluctuated, a perfect illustration of Heisenberg's uncertainty principle operating in its most extreme form. As I've noted before, this hypothetical state is often called quantum foam. On these microscopic Planck scales, virtual particles, tiny wormholes connecting disparate points in space and time, and even virtual black holes could have spontaneously erupted from the vacuum, only to vanish in an instant. These Planck-scale black holes would have been incredibly small, but would have possessed immense mass. They would have evaporated almost immediately due to Hawking radiation, releasing their energy back into the universe. If this depiction is accurate, these transient, fleeting quantum black holes could be described as the very first objects to exhibit any kind of individuality and structure within that primordial, undifferentiated chaos. The Planck epoch, this inconceivable tempest in the very fabric of reality, was astonishingly brief, lasting only 10 to the power of minus 33 seconds. As the universe began its expansion, for reasons not yet fully understood, its temperature and energy density plummeted.
The moment the temperature dropped just below the critical Planck value, the first great event in cosmic history took place. The initial shattering of that perfect, ideal symmetry. One component of the unified superforce, gravity, the weakest and most extensive of the forces, could no longer be sustained within this union, as there was insufficient energy to maintain its connection to the others. Consequently, gravity separated and embarked on its own independent existence, becoming the force that Einstein's theories describe. This event signifies the first phase transition in the history of the cosmos, marking the end of the Planck epoch and heralding the dawn of a new era, the grand unification epoch. With this, the world took its first small but definitive step away from incomprehensible chaos and toward the ordered structure you observe today. Every great empire, regardless of its power, ultimately falls. In the earliest moments of our universe's history, there was a single, flawless empire of fundamental forces, where all interactions were identical and followed a single governing law. Yet, its reign was short-lived. The first collapse of this empire, the first great schism, happened a minuscule fraction of a second after the theoretical start of time, when the universe was merely 10 to the power of minus 43 seconds old. That moment, when gravity split from the other three forces, forever shaped the fundamental character of our cosmos, dividing reality into Einstein's domain of geometry and the separate domain of quantum mechanics. To grasp the full weight of this event, it is helpful to spend a bit more time on the idea of a phase transition, a phenomenon you constantly encounter in daily life. The most straightforward and vivid example is water. When you heat liquid water to 100 degrees Celsius, it undergoes a phase transition and transforms into steam. While its chemical makeup, H2O, remains unchanged, its physical properties and internal structure are altered dramatically, causing steam to behave in a completely different manner than the liquid it came from. You can think of it like what happens when you cool water to 0 degrees Celsius. It undergoes a phase transition, becoming ice, which is a solid, crystalline structure with entirely new properties. At that precise moment of change, the very arrangement of matter is abruptly reconfigured. As the early universe expanded and cooled, it passed through a whole sequence of similar phase transitions. The difference is that it wasn't the state of ordinary matter changing because what we know as matter didn't exist yet. Instead, the vacuum itself was transforming, altering the laws of physics and the very nature of the fundamental forces. The first and most monumental of these transitions occurred as the Planck epoch concluded. With the universe expanding and cooling, its temperature dipped just below the Planck value of 10 to the 32nd power Kelvin. At this point, there was insufficient energy to hold all four fundamental forces in their unified, symmetrical state. Consequently, gravity, the force that appears weakest to us today, was the first to break away. It established itself as an independent interaction, defined by the geometry of spacetime, while the strong, weak, and electromagnetic forces remained bound together for a while longer. This separation marked the dawn of the grand unification epoch, which physicists often refer to as the GUT epoch, an abbreviation for Grand Unified Theory. This era stretched from approximately 10 to the minus 43rd power seconds to 10 to the minus 36th power seconds. Throughout this period, the universe continued its rapid expansion and cooling. By the epoch's end, the temperature had fallen to around 10 to the 28th power Kelvin, a state still incomprehensibly hot, yet 4 orders of magnitude cooler than in the Planck era. So, what was the universe like during this time? It was a vast expanse filled with an extremely hot, dense plasma. However, this was not the plasma you might imagine, made of protons and electrons.
the familiar particles of our standard model most likely hadn't formed into stable states yet. Grand unified theories proposed that the cosmos was instead populated by hypothetical, exotic, and unbelievably heavy particles. The principal actors during this epoch were the theoretical X and Y bosons, which are believed to have mediated the single unified electronuclear force. Their predicted mass is staggering, estimated to be about 1 trillion times that of a proton. It is for this reason that we could never hope to produce them, not even in our most powerful particle accelerators, as the required energy levels are simply beyond our reach. These particles possessed a truly astonishing characteristic. They had the ability to transform the fundamental constituents of matter into one another. Grand unified theories suggest that X and Y bosons could convert quarks, the building blocks of protons and neutrons, into leptons, like electrons and neutrinos, and could also reverse the process. In the universe we inhabit today, this is absolutely forbidden. Quarks invariably stay quarks, and leptons remain leptons. During the grand unification epoch, however, that dividing line was fluid. This is a critically important concept that we will revisit when we explore one of cosmology's most profound questions: why the universe contains so much more matter than antimatter. The capacity of X and Y bosons to violate what is known as the conservation of baryon and lepton numbers might just hold the answer to this enduring mystery. Another strange prediction from grand unified theory involves the potential appearance of hypothetical particles called magnetic monopoles during this era. You are used to the fact that any magnet possesses two poles, a north and a south. If you were to slice a magnet in half, you wouldn't isolate the poles. You would simply create two smaller magnets, each with its own distinct pair. The concept of particles having just a single magnetic pole was first proposed by the physicist Paul Dirac back in 1931. Grand unified theories forecast that these magnetic monopoles should have been generated in immense quantities during the phase transition that concluded the grand unification epoch. They would have emerged as flaws in the fabric of spacetime, much like the imperfections that appear in ice crystals as water freezes. This presents a significant challenge because if magnetic monopoles did exist, they would be incredibly massive, stable, and quite simple to detect. Yet, after decades of dedicated searching, not a single one has ever been found. The complete absence of these particles in our observable universe has long been a major argument against grand unified theory. This enigma, dubbed the monopole problem, was in desperate need of an explanation. That explanation eventually arrived in the form of an idea describing the next and perhaps most spectacular event in our universe's history, an event that took place precisely at the close of the grand unification epoch. As the universe's cooling trend continued, the unified electronuclear force, the combination of strong, weak, and electromagnetic interactions, grew increasingly unstable and approached another breakdown. Around 10 to the minus 36th power seconds, the temperature hit a critical threshold, leading to the second great split. The strong nuclear force, the most powerful of the remaining interactions, separated from the electro-weak force. This event signified the end of the grand unification epoch. A leading hypothesis suggests this phase transition could have unleashed an enormous quantity of latent energy from the vacuum, which in turn ignited a period of incredibly rapid, exponential expansion known as cosmic inflation. This fleeting moment of immense growth would not only resolve the monopole problem by scattering the particles across a vast, now unobservable cosmic volume, making them practically undetectable, but it also provides an explanation for many other fundamental properties of our world that once seemed like mere coincidences. Therefore, despite its speculative foundations,
and its remoteness from direct experimental verification, the Grand Unification epoch holds a crucial position in our story of the cosmos. It provides a framework for understanding some of the deepest questions about the universe you and I live in. This era formed a crucial link between the bewildering physics of the Planck time and a new reality where the forces and particles familiar to you began to materialize. It was during this stage that the groundwork was laid for the eventual asymmetry between matter and antimatter. It is also possible that this epoch concluded with the trigger for cosmic inflation, an event that magnified the minuscule quantum realm to astronomical proportions and permanently defined the character of our universe as we leave the unified forces behind for an era that, while fleeting, altered everything. What if I were to tell you that at one point in our cosmic timeline, the universe expanded faster than the speed of light? This was an instant, many billions of times shorter than the blink of an eye, during which its size multiplied by trillions of trillions of trillions. A spatial region previously smaller than a proton ballooned in that moment to the size of a grapefruit, or perhaps even larger. This scenario may sound like science fiction, seemingly a direct contradiction of the fundamental physical laws established by Einstein. Yet this is not a fantasy. It represents the core tenet of one of modern cosmology's most significant and influential concepts, the theory of cosmic inflation. This idea is more than just an elegant hypothesis. It stands as a vital component in explaining why our universe has the structure you observe today. To grasp why such a seemingly radical proposal became necessary, you must revisit the classic Big Bang model and confront the puzzles it was unable to resolve. By the end of the 1970s, the standard cosmological model had achieved remarkable success. It provided a brilliant account of the universe's expansion. It predicted the existence and temperature of the cosmic microwave background, also known as relic radiation, which is the thermal energy that pervades the cosmos, and it accurately calculated the prevalence of light elements like hydrogen and helium. Despite these accomplishments, several profoundly difficult and fundamental questions lingered, acting like persistent flaws in an otherwise magnificent structure. The foremost among these is the horizon problem. When you observe the cosmic microwave background arriving from every direction, you find it to be astonishingly uniform. Its temperature is virtually identical across the entire sky, with variations of only 1 part in 100,000. This uniformity suggests that the early universe, at the roughly 380,000 year mark when this radiation was released, was in a state of nearly perfect thermal equilibrium. However, this presents a paradox. Two regions on opposite sides of the sky that you see today, for instance, due north and due south, were separated back then by a distance many tens of times greater than light could have traversed in the entire age of the universe at that point. This implies these areas could never have been in causal contact. They had no way to exchange information or energy to coordinate their temperatures. In the context of the standard Big Bang model, their identical temperatures appear as an unbelievable and absurd coincidence. Like two individuals who have never met somehow writing the exact same book, word for word. Next is the flatness problem. Einstein's general theory of relativity posits that spacetime can possess one of 3 geometries. It can be open, curved, like a saddle, closed, shaped like a sphere's surface, or flat, resembling a sheet of paper that follows ordinary Euclidean geometry. All of our current observations indicate that our universe is, to an exceptionally high degree of accuracy, flat. The difficulty here is that a flat geometry is an incredibly unstable condition. Any minuscule deviation from perfect flatness in the very early universe would have been dramatically amplified over 13.8 billion years of cosmic expansion. Had the initial density been even fractionally higher than the critical density, the universe would have collapsed back on itself long ago. Conversely, if it had been slightly lower, the universe would have expanded so quickly that galaxies would never have had the chance to form. The reality of our flat universe implies that its density in the first second of its existence had to be fine-tuned to an accuracy of 15 decimal places, an act comparable to balancing a pencil on its point for billions of years, which the standard Big Bang model simply accepted as a given without explanation. Then, in the early 1980s, a compelling solution to these issues was put forward by young physicists Alan Guth in the United States and independently by Andrei Linde and Alexei Starobinsky in the Soviet Union. They proposed that in the universe's first moments, specifically between 10 to the minus 36th and 10 to the minus 32nd power of a second, there was a brief but tremendously powerful phase of ultra-fast exponential expansion. This period was named inflation. How does this theory resolve the problems? Inflation takes an infinitesimally small, microscopic patch of the early universe, a region so tiny that all its components were in causal contact and could achieve thermal equilibrium, and then, in a mere fraction of a second, stretches this uniform area to immense astronomical scales. The entirety of your observable universe today is just one small fraction of that original microscopic region. This elegant mechanism solves the horizon problem. The remarkable consistency of the cosmic microwave background is no longer a coincidence, but a direct result of our entire world originating from a single, tiny, thermally connected space. Inflation also provides a solution to the flatness problem. Picture the surface of a balloon as it inflates. When the balloon is small, its curvature is very apparent. But as it expands to a gigantic size, its surface would seem practically flat to a small ant crawling upon it. In a similar way, inflation stretched any initial curvature of space-time so profoundly that, on the scale of our observable universe, it has become indistinguishable from being perfectly flat. This leaves us, however, with a new question. What incredible force could have possibly powered such a monumental process? You might wonder, what could have driven space to expand at such a phenomenal rate, seemingly breaking the universal speed limit? It's crucial to recognize that while special relativity prevents objects from traveling through space faster than light, it places no restrictions on the expansion of space itself. The prevailing hypothesis suggests that the driving force behind this inflation was a unique theoretical scalar field known as the inflaton field, which possessed the remarkable ability to exist in what is called a false vacuum state. Unlike the ordinary vacuum we know, which represents the lowest possible energy state, a false vacuum is a temporary, metastable condition with an incredibly high energy density. This false vacuum energy exhibited a peculiar characteristic: negative pressure. According to Einstein's equations, this negative pressure generates a powerful gravitational repulsion, effectively an anti-gravity force, which is precisely what propelled the universe into its phase of exponential expansion. The inflationary period concluded when the inflaton field transitioned from its unstable false vacuum state to its true, stable state of low energy, much like a ball settling in a valley after rolling down a hill. At this point, the rapid expansion stopped, but the immense energy stored within the inflaton field did not simply vanish. Instead, it was unleashed in a process called reheating, transforming into a torrent of hot, fast-moving particles and radiation that filled the cosmos, creating the primordial soup of the classic Big Bang model. Therefore, inflation doesn't contradict the Big Bang.
It actually sets the stage for it. Furthermore, the theory of inflation introduced an even more staggering concept: the possibility of eternal inflation and the multiverse. In the model proposed by Andre Linde, the inflaton field's behavior can vary across different expanses of the cosmos. Although inflation ceased in our cosmic neighborhood, allowing our universe to form, it may continue indefinitely in other far-flung regions. Within this eternally inflating sea, bubbles could spontaneously form where the expansion halts, with each bubble representing the birth of an entirely new universe. Our own universe might just be one of countless such bubbles in a perpetually growing multiverse, where the fundamental laws and constants of physics could be entirely different. Inflation is thought to have ended at around 10 to the minus 32nd power seconds, leaving behind a cosmos that was vast, flat, and uniform, but also virtually empty and cold. It was the subsequent reheating process that filled this void with a hot plasma of particles, heralding the start of the next major phase, the electroweak epoch. In this way, a fleeting moment of hyper-expansion not only addressed profound cosmological questions, but also revealed a reality far more magnificent and intricate than we ever could have conceived. I want you to try to imagine a reality without mass, a universe where all the fundamental particles that constitute matter are weightless. In such a place, atoms could never form, as electrons would not be bound to nuclei. Without atoms, there could be no complex structures like planets or stars, and certainly no life as we know it. All particles would simply streak through the void at the speed of light, unable to combine into anything stable. This is very likely how our own universe appeared in the moments immediately following the end of cosmic inflation. However, in a mere fraction of a second after its beginning, a profound transformation occurred. The universe became suffused with an invisible, all-pervading field that behaves like a kind of cosmic syrup. As particles moved through this field, some encountered a form of resistance, thereby gaining inertia, or mass, while others passed through it completely unhindered. This pivotal event in cosmic history, the moment particles acquired their mass, took place during what is known as the electroweak epoch. This era began just after inflation and reheating concluded, at roughly 10 to the minus 32nd power seconds. The universe at this stage was an unimaginably hot and dense soup of elementary particles, quarks, leptons, and the interaction-carrying gauge bosons, with temperatures soaring to 10 to the 15th power Kelvin. While gravity and the strong nuclear force had already split into distinct phenomena in a prior epoch, the remaining two fundamental forces, electromagnetism and the weak nuclear force, were still fused into a single, unified, electroweak force. Here, our scientific footing becomes much more secure than in the discussions of previous cosmic eras. The physics of the electroweak epoch, unlike the highly speculative theories about the Planck era or grand unification, is not only something we can describe mathematically, but also something we can partially replicate in laboratories here on Earth. Conditions akin to this period are generated during particle collisions at the Large Hadron Collider, or LHC, at CERN. This is not conjecture. It is a field of high-energy physics validated by decades of experiments and celebrated with a Nobel Prize. The theory that describes this unification of forces was formulated in the latter half of the 20th century by three brilliant physicists: Steven Weinberg, Abdus Salam, and Sheldon Glashow. Their work demonstrated that at energies exceeding 100 giga-electron volts, the electromagnetic and weak interactions become indistinguishable.
They merge into a common structure mediated by 4 massless particles, 3 W bosons and 1 B boson. In this high-energy state, the weak force had a range as infinite as electromagnetism, but this condition of perfect symmetry was ultimately unstable. As the cosmos continued to cool and expand, it was poised for another fundamental shift, a phase transition that would permanently divide the electro-weak force. This presented a significant theoretical hurdle because the equations governing this unified force demanded that its carriers, the W and Z bosons, have no mass. Yet experimental evidence clearly showed they are extraordinarily heavy, weighing nearly 100 times more than a proton, which is precisely why the weak interaction operates over such a short distance. How could these particles gain mass without breaking the fundamental symmetries of the theory? The solution to this puzzle was first suggested back in 1964 by several groups of physicists, with the most renowned proposal coming from British theorist Peter Higgs. He theorized the existence of an entirely new type of field, which now bears his name. The Higgs field possesses a remarkable property that sets it apart from fields like the electromagnetic one. Its lowest energy state occurs not at a value of 0, but at a distinct non-zero value. This implies that even in the most perfect vacuum, the Higgs field is active, permeating the entirety of the universe. During the initial moments of the electro-weak epoch, the universe was so intensely hot that this vacuum energy was effectively 0, leaving the Higgs field inactive and all particles massless. However, once the temperature of the cosmos fell below a critical threshold, around 10 to the 15th power Kelvin or a quadrillion degrees, a phase transition took place, much like steam condensing into water. In that instant, the Higgs field assumed its non-zero value across all of space, and from that point forward, various particles started to interact with it in unique ways. Let me offer another analogy to clarify this. Imagine the Higgs field is like a room filled with people at a party, spread out evenly. If a stranger walks in, they can move through the crowd with little resistance, easily getting from one side to the other. This is akin to a massless particle, like a photon, which doesn't engage with the Higgs field and travels at the speed of light. Now, suppose a major celebrity enters that same room. Guests would immediately flock around them, slowing their movement and making it much harder to navigate the space. This individual becomes more inert, mirroring a massive particle, such as a W boson or an electron, whose mass is not an innate property, but rather a reflection of how strongly it interacts with the Higgs field. This brilliant concept, known as the Higgs mechanism, not only explained the origin of particle mass, but also predicted an undiscovered particle. In the same way the photon is the quantum of the electromagnetic field, the Higgs field required its own quantum, the Higgs boson, which you can visualize as a local excitation in the field, like a rumor creating a wave of density as it spreads through the crowd. For nearly half a century, finding this particle was a primary objective of high-energy physics, a quest that culminated on July 4, 2012, when scientists at the Large Hadron Collider announced they had found a particle with properties matching the predicted Higgs boson. This critical phase transition, called electroweak symmetry breaking, took place approximately 1/trillionth of a second, or 10 to the power of -12 seconds, after the birth of the universe. In that moment, the unified electroweak force split into the two forces you know today, electromagnetism, carried by the massless photon, and the weak nuclear interaction, mediated by the massive W and Z bosons. With this separation, all 4 fundamental forces of nature now existed independently, essentially completing the foundational architecture of our world. The electroweak epoch, therefore, represents a period of immense transformation. It started with a reality of massless particles and a single, unified force, and concluded with a universe where particles possessed mass and the forces were distinct. The cosmos had cooled to a mere quadrillion degrees, becoming slightly less exotic and more recognizable. All the necessary ingredients to construct matter as you know it were now present. Everything surrounding you, from mountains and trees to your own body, is made of this matter, which is built from atoms, themselves composed of electrons, protons, and neutrons, which are made from fundamental particles known as quarks. And yet, as predicted by Paul Dirac and later proven, every matter particle has an antimatter twin. This evil twin possesses the same mass, but has an opposite electric charge and other opposing quantum properties. The electron has its positron, the proton its antiproton. Both our theories and experiments confirm that at high energies, matter and antimatter always emerge in pairs, with pure energy yielding equal quantities of each. Following this principle, the hot, early universe should have created them in absolutely identical amounts. But if that were true, they would have mutually annihilated as the cosmos cooled, leaving behind a sterile universe filled only with photons. The fact that we are here to even contemplate this question is undeniable proof that this perfect symmetry was broken, and that some primordial glitch produced a tiny but crucial surplus of matter over antimatter. This fundamental imbalance most likely emerged during an era when the universe was a roiling inferno of matter's most basic constituents. I'm referring to the quark epoch. This period commenced just after the electroweak symmetry breaking at roughly 10 to the negative 12 power seconds and concluded at 10 to the negative 12 power seconds, negative 6th power seconds, a mere 1/1,000,000th of a second after the dawn of time. As the cosmos continued to expand and cool, its temperature remained staggeringly high, measuring in the trillions of degrees. Under such energetic conditions, stable protons and neutrons simply could not form. Instead, the universe was permeated by an exotic state of matter that physicists refer to as a quark-gluon plasma, or what you might vividly picture as a quark soup. In the cool, contemporary universe we inhabit, quarks are never observed in isolation. They are perpetually locked within larger particles known as hadrons, such as protons and neutrons. The strong nuclear force that binds them possesses a peculiar quality. Unlike gravity or electromagnetism, its strength increases with distance. Attempting to separate two quarks is akin to stretching a rubber band. The more you pull, the more powerfully they are drawn back together. If you were to apply enough energy to snap this bond, that energy wouldn't liberate the quarks. Instead, it would transform into a new quark-antiquark pair, creating two new hadrons rather than two free quarks, a phenomenon called confinement. However, the extreme environment of the quark epoch was entirely different. The sheer energy of the particles in this primordial soup overwhelmed the confining force, allowing quarks and gluons, the carriers of the strong interaction, to move about with almost complete freedom, much like ions and electrons in conventional plasma. This isn't merely a theoretical construct. Scientists have successfully recreated this state of matter for fleeting moments in experiments. At both the relativistic heavy ion collider at Brookhaven National Laboratory and the Large Hadron Collider at CERN. By smashing the nuclei of heavy elements like gold or lead together at nearly the speed of light, they have given us a basis to discuss the properties of this primordial substance with a high degree of confidence. It was within this seething cauldron that the pivotal events determining the universe's destiny must have occurred. As I've noted before, the standard model of particle physics suggests that pairs of quarks and antiquarks, along with leptons and antileptons, should have been continuously created and annihilated in this plasma. Yet observations reveal that this isn't what transpired. For every proton or neutron existing today, there are approximately 1 billion photons of cosmic microwave background radiation, the lingering echoes of that immense annihilation. This evidence implies that, in the very beginning, for every billion antiparticles, there existed 1,000,000,001 particles of matter, all because of some unknown process.
This minuscule asymmetry, just one part in a billion, is the very foundation for all the material reality you see around you. The question of its origin, known as the baryon asymmetry problem, remains one of the most profound unsolved puzzles in modern physics and cosmology. While we lack a definitive answer, we have a clear set of criteria for how this imbalance could have arisen, thanks to the brilliant Soviet physicist and human rights advocate Andrei Sakharov. As early as 1967, he proposed 3 conditions that must have been met in the early universe. The first of Sakharov's conditions is the existence of processes that violate the conservation of baryon number. You can think of the baryon number as the total count of quarks minus the total count of antiquarks. In our world, this number is strictly conserved. Quarks don't simply vanish or morph into other types of particles. However, as you may recall from our discussion of the grand unification epoch, the hypothetical X and Y bosons could have facilitated such transformations. For any excess of baryons to have formed at all, this rule had to be broken.
The second condition demands the violation of what are known as C and CP symmetry. C symmetry, or charge conjugation, posits that the laws of physics should be identical for both particles and antiparticles. The more complex CP symmetry, or combined parity, essentially states that physical laws should remain unchanged if you swap all particles for antiparticles, while also reflecting the universe in a mirror. For many years, these symmetries were thought to be absolute, but a Nobel Prize-winning discovery in 1964 experimentally proved that the weak interaction does, on rare occasions, violate CP symmetry. This violation was critical, because without it, any process that generated an excess of matter would be perfectly counterbalanced by a symmetric process creating an identical excess of antimatter, leading to a net result of 0. The third and final of Sakharov's conditions is a departure from thermal equilibrium. Had the early universe remained in a state of perfect equilibrium, all reactions would have proceeded at equal rates in both forward and reverse directions. Any surplus of matter that arose would have been instantly annihilated by the corresponding reverse reaction. The universe had to expand and cool rapidly enough to essentially freeze the imbalance in place, preventing it from reverting to a symmetric state.
So, we possess the recipe for creating a matter-dominated universe, but we are still uncertain about the specific chef and ingredients involved. Although the standard model does incorporate CP symmetry violation, the effect it predicts is far too weak to account for the observed billion-to-1 surplus of matter. This strongly suggests that the solution lies in physics beyond our current understanding. Numerous hypotheses have been proposed, with one possibility being that the answer is connected to the decay of those same super-heavy X and Y bosons predicted by grand unified theories. Another possibility is that this imbalance is linked to the properties of neutrinos, which have been discovered to also exhibit symmetry violation. Some theories even speculate that antimatter wasn't destroyed at all, but was merely isolated from our part of the universe, existing today in distant, unreachable areas in the form of anti-stars and anti-galaxies. Nevertheless, most astronomical observations render this possibility highly unlikely, so the riddle of baryon asymmetry persists without a definitive answer. While physicists continue to puzzle over this problem, the universe in our cosmic story carries on with its relentless cooling. The era known as the quark epoch is drawing to a close.
The energy possessed by the particles in the primordial quark soup has fallen below the level needed to defy the ever-growing power of the strong nuclear force. This period of liberty is over, and the strong force is starting to take control, setting the stage for the assembly of the first permanent building blocks of our world as the Hadron epoch commences. Picture particles that are condemned to an eternal state of confinement, forever hidden from view as individual entities, regardless of our efforts to isolate them. The more intensely you attempt to pull them apart, the more powerful the force becomes that snaps them back together. These are the quarks, the elementary constituents of all nuclear matter. Their strange, unbreakable imprisonment within larger particles began approximately 1/1,000,000th of a second, or 10 to the minus 6th power seconds, after the birth of the universe. That instant signaled the end of the free-roaming quark soup and the beginning of a new chapter, the Hadron epoch, which witnessed the formation of the first familiar composite particles, protons and neutrons. To grasp the fundamentals of this transformation, you must again consider the peculiar and counterintuitive behavior of the strong nuclear force. We are familiar with fundamental forces like gravity and electromagnetism weakening as distance increases. The farther the Earth is from the Sun, the weaker its gravitational attraction becomes, and the farther you are from a magnet, the weaker its magnetic field feels. The strong force, which binds quarks together, operates in precisely the opposite manner. At extremely short distances within a proton, quarks act almost as if they were free particles, a phenomenon scientists call asymptotic freedom. However, if they try to move away from each other, the force between them doesn't diminish but actually intensifies. You can visualize this force as an invisible yet incredibly strong elastic band stretched between the quarks. The more you stretch this band, the more energy it accumulates and the more effort is needed to stretch it further. Should you inject enough energy into this system in an attempt to snap the band and liberate a quark, something extraordinary occurs. The energy you've supplied reaches a critical point where, in accordance with Einstein's renowned equation E equals mc squared, it converts into a brand new pair of particles, one quark and one antiquark. This new pair immediately latches on to the broken ends of your band, so instead of achieving two free quarks, you are left with two completely new and fully formed hadrons. This phenomenon, which I've touched upon before, is known as confinement, or more specifically, color confinement. Quarks are fated to exist only in groups, forming combinations where their color charges, the strong force's equivalent of electric charge, collectively cancel each other out. Throughout the quark epoch, the universe's temperature and energy density were so immense that this binding energy was easily overcome, allowing quarks and gluons to exist in a deconfined state called a quark-gluon plasma. However, as the cosmos expanded and cooled, the average energy of these particles decreased. At roughly 10 to the minus 6th power seconds, the temperature fell below a critical point of about 2 trillion degrees Celsius. The energy within the quark soup was finally too low to overcome the powerful elastic band of the strong force, triggering another fundamental phase transition in the universe. Free quarks and gluons condensed, combining to form composite particles called hadrons. The term hadron originates from the Greek word hadros, which means strong or massive, and it applies to any particle that is affected by the strong nuclear interaction. In that moment, a whole menagerie of these particles burst into existence, often referred to as a hadron zoo. They are categorized into two primary groups: baryons, which are composed of 3 quark combinations, and mesons, which are made of a quark-antiquark pair. The majority of these newly created hadrons, such as pions and kaons, were incredibly unstable and rapidly decayed into lighter particles. Yet, within this diverse population, Two specific types of baryons were destined to have a central role in the universe's subsequent evolution: protons and neutrons. These are the very components of every atomic nucleus, including the ones that form you and me. We now understand that a proton is made of 2 up quarks and 1 down quark, whereas a neutron consists of 1 up quark and 2 down quarks. During the Hadron epoch, vast quantities of protons and neutrons, along with their antimatter counterparts, antiprotons and antineutrons, filled the universe. These particles were in a constant cycle of creation through collisions and immediate annihilation with each other, which kept them in thermal equilibrium with the surrounding soup of leptons and photons. At that stage, protons and neutrons could also readily convert into one another. Because a neutron is slightly more massive than a proton, in our modern universe, a free neutron is unstable and decays into a proton, an electron, and an antineutrino in about 15 minutes. But during the Hadron epoch, the ambient energy was so high that the reverse reaction, a proton and an electron colliding to produce a neutron and a neutrino, was equally common. With these two processes balancing each other out, the populations of protons and neutrons were nearly identical. As the universe's cooling trend persisted, another significant event took place. The temperature dropped so low that the average energy of collisions was no longer sufficient to generate new proton-antiproton or neutron-antineutron pairs. While their creation came to a halt, their annihilation did not. It was at this point that the minuscule baryon asymmetry, born during the quark epoch, played its decisive role. In a cosmic cataclysm, nearly every hadron met its antimatter counterpart, converting their mass into a torrent of pure energy and radiation. A minuscule fraction, a mere 1 in a billion surplus of baryons, was left without a partner for this annihilation. From this remnant of surviving protons and neutrons, every bit of the baryonic matter you observe in the cosmos today was forged. As the Hadron epoch concluded, approximately 1 second after the dawn of time, the universe's temperature had fallen to around 10 billion degrees. While immensely hot by any standard, this was no longer sufficient to sustain the equal rate of reactions that transformed protons into neutrons and back again. Because a neutron possesses slightly more mass than a proton, its creation demands a greater energy investment, causing the cooling cosmos to favor the formation of the lighter protons. The perfect balance between neutrons and protons was broken, with the scales tipping decidedly toward protons. When these conversion reactions eventually tapered off, the universe was left with a composition of about 6 or 7 protons for every single neutron. This fixed ratio proved to be of paramount importance for the next phase in cosmic history: primordial nucleosynthesis, which would commence a few minutes later and forge the first light atomic nuclei. Ultimately, this specific proportion is why the universe you know is made of approximately 75% hydrogen and 25% helium. In this way, the Hadron epoch, though fleeting, lasting just a millionth of a second, was a profoundly pivotal period. It signified the shift from a reality dominated by fundamental yet unseen quarks to one defined by the protons and neutrons we recognize. During this time, nearly all antimatter was eradicated, preserving only the tiny surplus of matter that would become the foundation for everything to come. As the cosmos cooled and the production of new heavy particles ceased, the stage was set. But the saga of that first second was far from complete. With the heavy hadrons now formed and their antimatter counterparts almost entirely annihilated, the cosmic drama was cleared for a new cast of characters. At about 1/1,000,000th of a second into its existence, the universe became the domain of lighter, more nimble particles known as leptons, which are immune to the strong nuclear force. Among them were familiar electrons, but they were joined by far more enigmatic partners, neutrinos. These ethereal, nearly massless particles which stream through your body by the billion each second, were poised to play a crucial part in the early universe's narrative. The lepton epoch unfolded between 1/1,000,000th of a second and 1 full second after the beginning, a period of relentless expansion and cooling. The temperature plummeted from trillions down to about 10 billion degrees, creating an environment of incredible heat and density comparable to the core of a massive star. It was far too hot for stable atoms to form, yet it was no longer hot enough to forge new proton-antiproton pairs from pure energy. Instead, the cosmos was a roiling plasma of surviving protons and neutrons, a sea of photons, and a vast population of electrons, positrons, neutrinos, and antineutrinos, all in a state of thermal equilibrium. This equilibrium was sustained by ceaseless activity, resembling a pot of boiling water. Colliding photons would continuously generate pairs of electrons and their antiparticles, positrons, which would then almost immediately annihilate each other, transforming back into photons. Similar processes, driven by the weak interaction, were constantly creating and destroying neutrino-antineutrino pairs, maintaining a dynamic yet balanced state throughout the system. Yet, not all particles within this fiery plasma were on equal footing. The neutrino was a notable exception, distinguished by its profoundly weak capacity for interaction. Participating only in the weak nuclear force and gravity, it remains unaffected by both the strong and electromagnetic forces, making it a true phantom of the subatomic world. To stop a neutrino would require a lead shield several light years thick, and in the dense conditions of the lepton epoch, even these elusive particles were ensnared. They constantly collided with other particles, keeping them trapped and rendering the universe opaque to them, as if shrouded in a thick fog. As cosmic expansion proceeded, however, both the density and temperature of matter continued to decrease. With particles growing more distant from one another and their average energy diminishing, the likelihood of a neutrino interacting with anything else dropped dramatically. A pivotal moment arrived when the universe was about 1 second old and had cooled to 10 billion degrees. At this point, the cosmos had become so sparse that the average distance a neutrino could journey without an interaction, its mean free path, finally exceeded the size of the observable universe itself. At that very instant, the universe grew transparent to neutrinos, an event that physicists refer to as neutrino decoupling. This process is analogous to what transpired much later with photons, which separated from matter after 380,000 years to create the cosmic microwave background radiation. However, neutrinos accomplished this separation far earlier, and from that point forward, they ceased to interact with any other form of matter. Having broken free, these neutrinos embarked on an uninterrupted voyage through space, carrying with them a pristine record of the universe's temperature and condition when it was merely 1 second old. These primordial particles, which should still permeate the cosmos today, constitute what we call the cosmic neutrino background. This constitutes a far more ancient echo of the Big Bang, a snapshot that predates the cosmic microwave background by hundreds of thousands of years. Successfully detecting this background radiation would represent a monumental breakthrough for cosmology, offering us a direct glimpse into that first formative second. So, you might ask, why has this detection not yet been achieved? The challenge lies in the fact that after traveling through an expanding universe for nearly 13.8 billion years, these neutrinos have shed almost all of their initial energy. Their anticipated temperature today is a mere 1.9 Kelvin, which is less than 2 degrees above absolute zero. Because their energy is so incredibly low and their interaction with matter is so faint, capturing them presents a technical challenge of immense proportions. Yet, scientists are not deterred by this difficulty. Ambitious projects
such as the Ptolemy experiment, are being specifically engineered to make the first ever attempt to detect these phantom-like remnants from the universe's first second. Let's journey back to that nascent cosmos. Just after the neutrinos decoupled from all other matter, another pivotal event unfolded. As the temperature continued its downward trend, it fell below the point required for photons to generate electron-positron pairs. While their creation ceased, their annihilation persisted, with nearly all electrons and positrons finding one another and converting into photons, which in turn slightly reheated the universe. And just as occurred with baryons, a minute surplus of electrons managed to survive this process. This very excess was essential for the later neutralization of the proton's electric charge, which allowed for the formation of electrically neutral atoms. In a universe without this surplus, our world would be composed solely of positively charged nuclei, and the existence of chemistry would be impossible. As the first second concludes, so does the lepton epoch. The universe has now cooled to 10 billion degrees and is composed of a definite, unchangeable number of protons and neutrons, a residual amount of electrons, a vast ocean of photons, and the freely traveling decoupled cosmic neutrino background. All the essential ingredients for atom formation are now present. The fundamental forces have all separated and now function according to the laws familiar to us today. Particles have acquired their mass, and the crucial imbalance between matter and antimatter has been firmly established. You might think the primary action is over, but it has only just begun. The three most chaotic and swift acts of this cosmic play have reached their conclusion, setting the stage for the slower yet equally vital process of building the first atomic nuclei. Only a single second has elapsed. During this time, light, traveling in a vacuum, covers just under 300,000 kilometers, a distance shorter than that between the Earth and the Moon. While this is an almost imperceptible moment for us, for the universe, it was an entire eternity. This first second was packed with more fundamental changes than it would undergo in all the billions of years to come. In that single second, the universe completed an extraordinary transformation. It evolved from a bewildering realm of exotic quantum gravity, where time and space might not have even settled into their final forms, into a relatively comprehensible world of elementary particles, poised to begin the construction of matter. Let's pause here at this 1-second milestone, reflect on the path we've traced, and consider the mysteries this crucial moment has left for us to solve. Let's re-examine this astonishing timeline, this time from a broader perspective. Our exploration started at the Planck Wall within the Planck epoch, a period lasting up to 10 to the negative 43rd power seconds. This was a reality of perfect symmetry, where the four fundamental forces were combined into a single superforce, and spacetime itself was possibly a turbulent quantum foam with numerous dimensions. Following this was the grand unification epoch, during which gravity was the first force to break away and become distinct. The strong, weak, and electromagnetic interactions, however, remained fused together. In this era, the universe was filled with hypothetical super-heavy particles known as X and Y bosons, which had the ability to convert quarks into leptons. Toward the end of this epoch, around 10 to the negative 36th power seconds, what was likely the most significant event in cosmic history took place: cosmic inflation. In a mere fraction of a second, the universe underwent an exponential expansion, ballooning in size by dozens of orders of magnitude,
This inflationary process smoothed out any initial irregularities, rendered the universe almost perfectly flat, and imprinted the subtle quantum fluctuations that would eventually grow into the seeds of all future galaxies. Once inflation concluded, the electroweak epoch commenced, a time when the strong interaction had already separated, leaving the electromagnetic and weak forces still unified. It was during this period that the universe underwent another profound transformation: the breaking of electroweak symmetry. The Higgs field activated across the cosmos, granting mass to most elementary particles, and causing the final two forces to diverge. This led into the quark epoch, a time when the universe was a dense quark-gluon plasma. It was in this primordial soup that the enigmatic process of baryon asymmetry occurred, establishing the tiny but momentous surplus of matter over antimatter that defines our existence, before giving way to the hadron epoch at roughly 1/1,000,000th of a second. As the universe cooled, quarks and gluons became confined within protons and neutrons, and nearly all antimatter was eliminated, leaving behind the slight surplus that forms all the visible matter you see today. This was followed by the lepton epoch, which ended as the first second drew to a close. Throughout this phase, like particles like electrons and neutrinos were dominant, leading to a pivotal event: neutrino decoupling. This process created the most ancient relic of the Big Bang that we could ever hope to observe. So, what was the state of the cosmos precisely at the 1-second mark? It was an environment profoundly different from anything familiar to you. The portion of the universe we can observe had expanded from a point of infinitesimal size into a sphere, roughly 10 light-years in radius. This volume was suffused with an intensely hot, dense, and opaque plasma of protons, neutrons, electrons, and a vast sea of photons, with its temperature having fallen to 10 billion degrees. At this point, the proportion of protons to neutrons became fixed at approximately 6:1. These conditions established the foundation for the next crucial phase, the era of primordial nucleosynthesis, set to commence just a few minutes later. In that brief interval, before the cosmos cooled any further, protons and neutrons started to merge, forging the first light atomic nuclei. This process primarily yielded helium-4, along with minute quantities of deuterium, helium-3, and lithium-7. However, the creation of the first stable, neutral atoms was still a distant event, nearly 380,000 years in the future. But how is it possible for us, nearly 13.8 billion years later, to investigate these ancient occurrences and test our theories about that impenetrable primordial state? Lacking a time machine, we rely on other, equally potent instruments, the echoes from those remote events that continue to reach us. The most renowned of these is the cosmic microwave background, or CMB, which is the residual thermal radiation that permeates all of space. This represents our earliest image of the cosmos, light released when the universe was 380,000 years old, and by analyzing its faint temperature variations, we can infer a great deal about the initial conditions established by inflation. Yet, the cosmic microwave background has its limits. It cannot reveal what happened before that moment, because the earlier universe was completely opaque to light. To probe deeper into the past, we require a different kind of window. As I've mentioned, that window is the cosmic neutrino background. These neutrinos separated from matter when the cosmos was just 1 second old, so detecting them would grant us a direct observation of the universe at that exact instant. Such a discovery would enable us to verify our models of cosmic expansion and cooling with extraordinary precision. There is yet another, perhaps even more formidable method for peering into the very beginning: gravitational waves. Unlike light or neutrinos, these ripples in spacetime interact very weakly with matter, meaning that gravitational waves produced during the first moments of inflation or the grand unification epoch should arrive here virtually unaltered. They are pristine messengers, carrying direct information about the most extreme physical processes imaginable. Although our current detectors, like the Laser Interferometer Gravitational Wave Observatory, or LIGO, and Virgo, are not yet sensitive enough to register this primordial background. Fortunately, future observatories such as the space-based Laser Interferometer Space Antenna, known as LISA, are being specifically designed to achieve this goal. The eventual detection of these primordial gravitational waves would spark a true revolution, launching the age of gravitational wave cosmology. We must also consider the profound mysteries that may have been forged in that first second, such as the nature of dark matter, which accounts for about 27% of the universe's mass energy. It's possible that dark matter particles emerged during a phase transition in this era, or that they are primordial black holes, hypothetical objects formed from the collapse of incredibly dense regions at the dawn of time. Ultimately, that first second established the governing principles for the entire subsequent history of the cosmos. It fixed the number of dimensions in our space, defined the fundamental forces, determined the composition of matter, and, through a minuscule asymmetry, made your very existence possible. We arose 13.8 billion years later on a small planet around an ordinary star, yet every particle in our bodies was shaped by those chaotic, fleeting initial moments. In studying them, we seek to answer not just how the universe is structured, but also the deeper philosophical question of why it is this way and not some other way. This expedition to the beginning of time, filled with breathtaking discoveries and even greater puzzles, has only just begun. It may be that the answers you and I are searching for are already streaming toward us from every direction, carried by ghostly neutrinos and the subtle ripples of space-time itself. We just have to learn how to listen. Imagine a paleontologist carefully excavating ancient layers of sediment. They don't see living creatures or hear their calls. Their only evidence consists of fossilized bones, preserved footprints, and the imprints of ancient plants. From these silent and scattered fragments, they meticulously reconstruct an entire lost world. In a very similar fashion, cosmologists like me operate as cosmic paleontologists. While we cannot journey back to the first second, we possess our own unique set of fossils and relics, the fundamental imprints that those turbulent, primordial events left upon the very fabric of the universe. By analyzing these cosmic remnants, we can recreate with astonishing accuracy the conditions that existed when our entire world was younger than a single heartbeat. Of all the cosmic artifacts from the dawn of time, the most renowned is undoubtedly the cosmic microwave background, also known as relic radiation. You can think of it as the universe's very first photograph. This is the most ancient light observable to us, released when the cosmos was merely 380,000 years old. Prior to this moment, the universe existed as an opaque plasma of protons, helium nuclei, and unattached electrons, all under conditions of extreme heat and density. In this environment, photons were unable to travel far, constantly scattering off electrons in a manner similar to car headlights penetrating a dense fog. This all changed when the universe cooled to about 3,000 degrees. At that crucial temperature, electrons could finally bond with nuclei to create the first stable, neutral atoms in a process we call recombination. As this happened, the cosmic fog lifted, and for the very first time, the universe became transparent to light. The photons that had just scattered off electrons for the last time were now free to journey unimpeded through the expanding space.
Those are the very same photons we detect today as the cosmic microwave background, which has been cooled by cosmic expansion to a mere 2.7 degrees above absolute zero. This brings us to a critical question. How can an image captured when the universe was 380,000 years old reveal anything about what happened in its very first second?
The solution to this puzzle is found not within the light itself, but in its almost imperceptible variations. When you examine a map of the cosmic microwave background, like those created by missions such as the Planck satellite, you'll notice it isn't perfectly uniform. It is dappled with tiny spots, some of which are just 1/100,000th of a degree warmer than the average, while others are colder by the same amount. These minuscule fluctuations might seem trivial, but they represent our most precious repository of information. These spots are the imprints of density variations that existed in the primordial plasma, where hotter patches correspond to slightly denser regions and cooler areas to less dense ones. The origin of these density differences traces back to events within the first fraction of a second of the universe's existence. According to the theory of cosmic inflation, these variations began as microscopic quantum jitters in what is called the inflaton field, at a time when the entire observable universe was smaller than an atom. The inflationary process then stretched these quantum fluctuations to astronomical proportions, transforming them into the tangible, macroscopic seeds of all future structures. Following inflation, these density inhomogeneities triggered oscillations within the hot plasma, much like sound waves propagating through the air. Regions of greater density would compress and heat up under gravity's pull, only to be pushed apart and cooled by radiation pressure. These acoustic oscillations, the literal sounds of the infant universe, reverberated for 380,000 years. The map of the cosmic microwave background is, in effect, a snapshot of these sound waves, frozen at the instant light broke free from matter. By analyzing the scale, distribution, and intensity of these spots, we can essentially reverse engineer the instrument that played this cosmic chord. This allows us to determine the fundamental parameters of our universe with astonishing accuracy. We can calculate the universe's age at 13.8 billion years. Its geometry is almost perfectly flat, just as inflation predicts, and its composition of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. Crucially, the characteristics of these fluctuations align perfectly with the predictions of the inflationary model, offering indirect yet powerfully persuasive evidence that this phase of hyperexpansion did occur in the universe's first moments. However, we possess an entirely separate and independent cosmic relic, the observed abundance of light chemical elements. As you may know, our universe is made up of about 75% hydrogen and 25% helium by mass, with only trace quantities of other light elements. While stars fuse hydrogen into helium, they couldn't have produced even a tenth of the helium we see everywhere, even over billions of years.
So, where did all this helium originate? The solution once again is found in the early universe, though this time not in the first second, but within the initial few minutes, during a process known as primordial nucleosynthesis. As we've discussed, by the 1-second mark, the universe was composed of protons and neutrons in a ratio of approximately 6:1. During the subsequent 3 minutes, the cosmos was at the perfect temperature for protons and neutrons to begin fusing. They first formed nuclei of deuterium, which contains 1 proton and 1 neutron, and then helium-4,
with 2 protons and 2 neutrons. This entire sequence was a delicate race against time, beginning only when it was cool enough for deuterium to stabilize, and ending as the universe expanded and cooled to the point where particles could no longer overcome their mutual electrical repulsion.
It's truly remarkable that by using the established laws of nuclear physics and inputting the conditions thought to exist in those first few minutes, such as temperature, density, and that initial proton-to-neutron ratio, we can calculate the precise amounts of helium, deuterium, and lithium that should have been created. These theoretical calculations align with breathtaking precision to what we actually observe in the universe's oldest stars and most distant gas clouds.
This concordance is an incredible scientific triumph, confirming that our understanding of the physics governing the first second and the first few minutes is fundamentally sound. The agreement between predictions derived from 2 completely different sets of relics, the patterns in the cosmic microwave background and the quantities of light elements, gives us immense confidence in our overall cosmological model.
Therefore, what we have are potent, if indirect, lines of evidence. Much like fossilized bones and footprints allow paleontologists to reconstruct dinosaurs, these cosmic relics empower us to speak with great certainty about the existence and properties of the universe in its most ancient state. Every paleontologist holds out hope for a truly exceptional discovery, something akin to finding an insect perfectly preserved in amber, a relic from a bygone era. As cosmic paleontologists, you might wonder if a similar opportunity exists for us. Is it possible to capture not just a faint echo, but a direct, unaltered message from the universe's very first second? The answer is yes, but achieving it requires us to master the detection of the most elusive particles and the weakest vibrations in the fabric of reality itself. If you consider the cosmic microwave background to be a photograph of the infant universe and the prevalence of light elements to be its chemical signature, imagine what it would mean to acquire something even more profound. What if we could listen to its sound recording, or perhaps even analyze a seismogram of its earliest, most violent tremors? While this may seem like something out of science fiction, it is the central goal of cosmology's most ambitious frontier today, the search for primordial messengers. These messengers are particles and waves that originated in the tremendous furnace of the first second. They have traveled across the cosmos for eons, carrying their information to us almost perfectly intact, because they barely interacted with anything along their journey. Capturing them would effectively grant humanity new senses, enabling us to perceive the universe in ways we've never imagined. The most significant of these messengers is the cosmic neutrino background. As we've discussed, these neutrinos separated from all other matter when the universe was merely 1 second old. In contrast, photons remained trapped for another 380,000 years before the cosmos became transparent enough for them to travel freely. This means neutrinos offer a direct, unfiltered glimpse of the universe's condition at that initial moment. This isn't just a baby picture, it's more like an ultrasound, providing a snapshot of the embryonic cosmos. So, if this resource holds such invaluable information, why has it not yet been detected? The difficulty is rooted in the fundamental properties of neutrinos themselves. Their interaction with matter is so astonishingly weak that it's almost beyond comprehension. Furthermore, after nearly 13.8 billion years of journeying through an expanding universe, they have lost almost all of their initial energy, leaving them with a predicted temperature of just 1.9 Kelvin. This incredibly low temperature means their kinetic energy is minute, making the detection of such low energy, weakly interacting particles a task at the absolute limit of our technological capabilities. The challenge is comparable to trying to catch a single, pre-selected grain of sand in the heart of a tornado,
using nothing but a pair of tweezers while blindfolded. Despite these odds, experimental physicists are pressing forward, devising exceptionally clever methods to capture these elusive particles. One of the most promising initiatives currently under development is the PTOLEMY project. The concept behind it is both brilliant and elegant. Scientists intend to use a vast quantity of tritium, which is a radioactive isotope of hydrogen, as a detector. A tritium nucleus is inherently unstable and naturally decays, emitting an electron and an electron neutrino. The energy of this emitted electron has a very specific and well-defined upper limit. However, what happens if a relic neutrino, a traveler from the universe's first second, strikes a tritium nucleus? It can induce a reaction where the tritium absorbs the ancient neutrino and releases only a single electron. The energy of this particular electron would be just a fraction higher than the maximum energy possible in a normal decay. By identifying these rare, super-high-energy electrons, scientists could be certain they have finally captured a relic neutrino. Should this experiment prove successful, it would rank among the most significant scientific breakthroughs of the 21st century. We would, for the very first time, have a direct measurement of the universe's temperature when it was just 1 second old. This would also teach us more about the mass of neutrinos and could potentially open the door to entirely new realms of physics. The second type of primordial messenger is even more fundamental. It isn't a particle at all, but a disturbance in the very structure of spacetime. Primordial gravitational waves. We are already certain that gravitational waves exist. Observatories like LIGO and Virgo now regularly register powerful signals from the mergers of black holes and neutron stars. But these are astrophysical events from the modern universe. Cosmologists are pursuing a different prize: the faint gravitational wave background that has persisted since the first moments of creation. These waves would have been produced during the most extreme processes imaginable, such as the period of cosmic inflation or the phase transitions of the grand unification epoch. Since gravity interacts so weakly with matter, these waves should have reached us in their original, pristine condition, offering a direct imprint of the events that created them. There is, however, a significant challenge. We anticipate that this primordial background will be incredibly faint. While the collision of black holes produces a loud, distinct chirp in our detectors, the primordial background is expected to be a quiet, constant, and random hiss or hum, which is vastly more difficult to isolate from instrumental noise and other interference. Currently, the search for these waves is advancing on two major fronts. The first is the effort to detect them directly with a new generation of detectors. Future space-based observatories, such as LISA, the Laser Interferometer Space Antenna, a massive triangular formation of 3 satellites linked by laser beams, will possess the sensitivity required to potentially detect the low-frequency gravitational waves generated during the electroweak phase transition. The second strategy involves hunting for their indirect effects on the cosmic microwave background. Primordial gravitational waves passing through the early universe should have twisted the polarization of the microwave background's light in a very particular way, leaving behind a unique pattern referred to as B-mode polarization. The quest to find this specific signature has become a primary objective for many modern cosmological experiments, including the BICEP telescope, which operates from the South Pole. To capture this signal would be to find the ultimate confirmation of the inflationary theory, providing irrefutable proof and opening a gateway to physics at energies trillions of times beyond what the Large Hadron Collider can generate. We are truly on the cusp of a new age in our comprehension of the cosmos. Our progress has been monumental, taking us from merely observing stars with the naked eye to creating detailed maps of the cosmic microwave background. Now, we are learning to attune ourselves to the universe's whispers, endeavoring to catch the faintest murmurs from the void that have journeyed to us from the very first second of time. Each new cosmic messenger we learn to perceive, whether neutrinos or gravitational waves, gives humanity a new sense with which to explore reality. We are transitioning from staring at still photographs of the past to hearing its sounds and feeling its vibrations. When our receivers are finally tuned with perfect precision, what will we discover? What additional secrets about our own genesis will these primordial carriers of information unveil? The solutions to these puzzles will undoubtedly steer the direction of cosmology for the next several decades.